And good afternoon. I'm Byung-Ju, a graduate student from Korea University. Today, I'd like to talk about a new type of convolution for text classification, which is a convolution with dynamically generated convolution filters. Convolutional neural networks, CNN, has been very successful in natural language processing tasks, including text classification. And as all of you may already know, the main component of convolutional neural networks is a convolution operation. It extracts important information by checking whether there is important information and to what degree the important information is in the input. It is achieved by applying convolutional filters directly to the input and sliding along the input with a predefined function to get an output. So what is encoded in this convolution filter is that which information is to be extracted for the target task. So we thought that the role of convolution filter is very similar to a question because the goal of both of them is to extract the important information. So if we liken a convolution filters to questions, a convolution operation can be a behavior of asking questions. Similarly, the output of the convolution can be analogous to the answers to the questions from the input. So in this point of view, CNN can be likened to a player of 20 questions because there are multiple filters are in the CNNs, and there are stacked convolution layers is in the convolutional neural networks. So the motivation of our paper is that there exists a difference between humans and CNNs on their approach to this game of 20 questions. And CNN can be improved by taking a hint from the approaches of humans. So humans adaptively ask questions by considering the information they have obtained or as a prior. So if a person narrowed down the answer to a name of a person, he may not want to waste their opportunity asking questions such as, does that have 4 legs or does that have a tail? Instead, he would likely raise a question about more related to the origin or profession of the target. However, CNNs apply the same set of filters regardless of different outputs acquired from convolution operations. So no matter which values are obtained from a result of the first convolution layer, it does not have an effect in any second convolution. So this situation can be similar to a person is asking a number of legs of the target, even though they know that the answer is a name of a person. So we thought that this could be problematic, and CNN can be improved in their capacities by letting them to fully utilize the information they have obtained during the process of input processing. So we modeled this by dynamically generating filters conditioned on input and applying convolution operation with the dynamically generated ones. So we call it adaptive convolution. Our approach can be applied to any kind of existing CNNs. And among them, we choose 3 baselines. The first one is a CNN, which is a shallow layer CNN, which is proposed by Yoon Kim. And the other one is a densely connected CNN and deep pyramid-shaped CNN. For the test data set, we choose the 7 benchmark text classification data set, including 4 sentiment classification, which I believe that this paper is belong to this session. And 2 of them are topic classification, And the last one is ontology classification. So we observed that our approach improved all the baseline on every single data set as much as up to 2.6% on absolute scale. And on average, our model achieved 1.1% increasement over the baseline. So this result shows the efficacy of our approach, and this result would support our intuition. So the question comes down to these two questions. How to generate filters and how exactly to apply generated filters. So let's talk about the first one. As I mentioned earlier, we generate filters as a function of an input. More specifically, we run a bidirectional GRU and concatenate the hidden stage of the GRU and apply the self-attention mechanism on them. So we get a vector as the output. We use this output to create the convolution filters, so we named it a context vector. Once we obtain a context vector, we fed it to a multi-layer perceptron and use the outputs of it to generate the convolutional filters. So the easiest way to make convolution filters with this output is directly use them as convolution filters after reshaping them. So this is the first approach we proposed, and we named it full generation. However, there is a problem to this approach because this approach requires very large number of parameters. So the required number of parameters in this approach is proportional to the multiplication of context vector size and the number of filter weights. So if we assume that the layer of the MLP is a single and the size of the context is 300 and number of filter weights is 900 by taking 300 for inputs and taking 3 for window size, the total number of parameters required is 270,000. This may seem to not that big enough, but the things go different. We want to make 300 filters. In that case, the required number of parameters is nearly 100 million. So in this case, it can cause issues including memory issues in some environment. So to handle this, we propose the alternative using a hashing technique. The key idea of this hashing technique is to share some weight in generating filters, and it's the same to any other hashing techniques in deep neural networks. So this is how it works. We first give an ID to convolution filters, such as ID1, and hash them using different number of predefined hash functions. From the result of the hash function, we extract the candidate vectors to become a convolution filters from a predefined pool. This is the pool and it's very similar to word embedding because it is pre-initialized and return a vector from its corresponding index. For in this case, we return the index of 3 for the first hash function and 0 for the second hash function, and so on. We obtain convolution filters just by linearly combining them and reshaping them. So what we want to do is dynamically generate filters conditioned on input. So we use the outputs of the MLP, which takes the context vector, as a way to determine the degree of this linear combination. This kind of approach can reduce the number of parameters because you can set these weights for the combination with very small size. So we can generate filters only with 1,000 parameters. And the number of parameters required for generating 300 is less than 1,000,000. So additional parameters comes from this pool can be also set to very small size. We apply our convolution layer by layer. Once we obtain filters from its input, the generated input is directly applied to the input from where the filters are generated. And the output of this operation becomes the input to the next convolution layer, and this is repeated for all the entire network. So this is the point where our approach becomes different from previous works. In fact, there has been previous works which is targeted on generating filters conditioned on input, especially in computer vision. And most of them are targeted at tasks which involve two different inputs. So this is the first difference. But the biggest difference is that their approach creates filters in network level. Once they got an input, they process the input in CNNs and generate the filters wholly based on the final hidden state. And the generated filters are directly applied to the next convolutional neural networks at the same time. And to say more about our evaluation, but both two of us, our approach increased the performance of the baseline models and on every single data set. However, the difference between our two models is very small. The average gap between these two approaches only 0.1%, and this is quite small, so there is no difference between them in terms of performance. So I think that this result showed that our hashing technique can really effectively parameterize the full network. And moreover, our approach performs better than strong baselines, such as attention is included recurrent neural networks. And these are the results I would like to highlight from our analysis. This graph shows the different performance with different number of filters and with different depths. From this analysis, we found that very small number of filters are enough to acquire the best performance, and shallow depth is enough to acquire nearly best performance. In fact, only 3 filters are enough to obtain nearly the best performance when the baseline is combined with our approach. However, the baseline needs more than 100 filters. So this result shows that our approach actually creates the filters which plays a critical role in extracting features. So in conclusion, we propose an adaptive convolution for making CNNs to fully utilize the obtained information and can increase the performance. We show the efficacy of our approach based on evaluation and show that our approach can improve the baseline on all the data sets. And we believe that hashing technique we have proposed can shed light on model compression. In fact, this approach can be applied to compress the model with slight modification of it. And finally, we believe that weight generation technique is not only limited to convolution filters, but also can be expanded to other deep learning models, including recurrent neural networks and transformers. So we plan to apply our weight generation technique to these models in the future. And this is the end of my presentation, and thank you for the listening.
Thank you. Any questions? I did have a question. So you had like a few different CNN models that you used. Did you see any difference, like, on how much of an improvement you got depending on which one you used?
No,
Or, like the skin and the.
Yeah, actually, the shallow model which used the single layer has the biggest improvement over the baseline.
Do you think like anything about the model impacted that, or?
So actually, we found that all the baselines seem to converge to a certain